Hello, we are six semester students from RVC and we are part of the computer science and engineering branch. And as part of our experiential learning component under the subject cloud computing, we have implemented a project involving Kubernetes security analytics. Regarding what is Kubernetes and an introduction into Kubernetes, Adarsh is going to take over.
Yeah, so this is Adarsh here. So to begin with, this is the basic roadmap of what we'll be implementing now. So first we'll be running through what multi-master Kubernetes cluster setup is. Then we'll be going into Nginx development, and then we'll be going through the Calico node development, Falco and Kubernetes, Grafana and Prometheus. Finally, we'll be going through what recommendation systems are, and we'll be doing a hands-on implementation of whatever. So yeah, let's move on to the first slide. So to begin with, we'll be talking about what Kubernetes is. So Kubernetes is an open source container orchestration platform designed to automate the deployment, scaling, and management of containerized applications. It abstracts the underlying hardware and also allows developers to develop applications in a scalable and reliable manner. So coming down to what are the key concepts in Kubernetes. Some of the key concepts in Kubernetes are pods, services, deployments, and replica sets. So what are pods? Pods are the smallest deployable units in Kubernetes. So these represent a single instance of a running process in any cluster. So a pod can contain one or more containers, and this will be shared within a same network or a storage. Then comes a service. So what is a service? A service is an abstraction that defines a logical set of pods. At the same time, a policy which defines to access them. Then comes our deployments. So once we are ready with this, we'll define the desired state of the application of the pods and manage the deployment processes and ensure that the correct number of pods are replicas are running. So finally comes the replica sets. So what these replica sets do is they ensure a specified number of pods, and these pods which are running at a given time. So what we have to do here is they maintain the desired number of the pods regarding of any failure. So this is the basic overview of what Kubernetes is. So then coming to our multi-master Kubernetes cluster setup, we'll move on to the next slide. So here, what it contains is in a multi-master Kubernetes cluster, there are multiple master nodes that manage the state of the cluster. And then there are the worker nodes. So this setup enhances the availability, reliability of the cluster, and also it ensures that the cluster can continue to function even if one or more cluster fails at any point of time. So it ensures redundancy, availability, and also diversity. So coming down to what a master node does. So these nodes are responsible for managing the cluster state, as mentioned earlier, and also they include in scheduling pods on worker nodes and also maintain the cluster health, along with managing the API servers. So these are the key components of the master nodes, which I would like to summarize again. API server, controller manager, scheduler, and etcd, which is like a key value store for the cluster data. Then comes the worker nodes. So these worker nodes run the application workloads, and also these nodes where the pods are deployed are also managed by the master nodes. So this is the basic overview of what a multi-master Kubernetes cluster setup is. So then let's move on to our HA proxy load balancer. So we'll move on to the next slide. So yeah, before going to Nginx, we'll just run through what HA proxy load balancers are. So HA proxy load balancers are usually a reliable and high performance load balancer that can be used to distribute the traffic. So whenever there is huge traffic, we'll use something called as a load balancer to distribute the load across multiple nodes. So in the context of a Kubernetes cluster, a HA proxy can be used to balance the traffic between multiple master nodes. So this is very crucial for high availability in any cluster. So roles of the Kubernetes in this HA proxy are very important. This ensures the incoming request to the Kubernetes API servers, which are evenly distributed across all the available master nodes. So this is the main important factor. And also this distribution prevents any single master node from becoming a bottleneck. So it basically distributes the workload, and also it improves the overall resilience of the control plane. So this is the first part. Then coming to the configuration part, any HA proxy can be configured to monitor the health of any master nodes, at the same time route the traffic onto healthy nodes. So if a master node becomes unavailable at any point of time, a HA proxy automatically reroutes the traffic to the other available nodes, maintaining the availability of the cluster. So this is the key factor in the proxy load balancer. Coming down to what a Kubernetes and a Docker repositories are. So a Docker is a platform that enables developers to package applications into containers, then which are actually lightweight, portable, and also self-sufficient. So these applications are in two parts when coming down to our Kubernetes. So Kubernetes uses Docker at any runtime to run these containers within the pods, and then these Docker images which contain the applications and its dependencies are pulled from the repository and then used to create the containers within the same Kubernetes cluster. So this is the first part of the Docker. Then coming to what Kubernetes repositories are. So these are the storage locations where the Docker images and the Kubernetes configuration files such as YAML, JSON files, all of these are stored. So these repositories can be hosted on platforms such as Docker Hub, Google Container Registries, which is also called as GCR, and any private registries. So these Kubernetes clusters pulls the necessary images from all of these repositories, and finally it deploys the applications within the cluster. So this covers the Docker and Kubernetes repositories part. Let's move to the next slide. So coming down to what an Nginx web server deployment is. So Nginx is a versatile and high performance web server that can also function as a reverse proxy load balancer at the same time as a HTTP cache. So it is widely used for serving static content, handling web traffic for dynamic content, which is usually generated by application servers. So the two key important aspects of Nginx web servers are deployment in Kubernetes and scaling the updates. So in Kubernetes, Nginx can be deployed as a containerized application using a deployment resource, and also it manages the creation of the pods during the runtime, and also it ensures the desired number of replicas are always running. Then comes the second part, which is the scaling and the updates. Here, Kubernetes deployments allows you to easily scale up both vertically and horizontally, and also the web servers by adjusting the number of replicas. So this is where the scale out comes into picture. They also support rolling updates where new versions of the image can be deployed gradually with a zero downtime. So this is the first part. Then coming down to what Calico node deployment is. So Calico is a robust networking and network security solutions. So it's designed specifically for Kubernetes clusters. So it provides networking for containers, enabling communication between the pods and also between within the cluster. So this is like a communication service and also networking feature. Here there are two aspects, which is the networking feature and the network security. So coming down to what are the networking features? Calico assigns unique IP addresses to each of the pods and within the cluster, enabling them direct communication between the pods without the need for network address translation, which is also called as NAT. This simplifies the networking and also improves the performance for reducing latency and the overhead. And then it also supports BGP. BGP is nothing but Border Gateway Protocol. It allows us to integrate with existing network infrastructure and also provides high scalable networking for large Kubernetes cluster when you want to uh, expand it. Then comes the security part. There are a lot of policies at the same time. There are security features when it comes down to Calico. Here, Calico enables the creation of network policies that define how pods can communicate with each other and also with the external networks. These policies provide fine-grained control over the traffic flow and also restricting access to the sensitive services. So this is one of the key features where the data integrity comes into picture. And also the some of the features are it provides in IP encapsulation, WireGuard encryption for secure inter-node traffic, and also it hosts endpoint policies to secure the entire cluster environment. So this comes down to what security features it provides, and also it is very uh, rich in high performance. It also delivers high throughput, low latency, and there is no bottleneck for any application. So this is through minimal packet processing over it and also efficient routing. So this was a gist of the first roadmap. Then let's move on to the next phase.
So, hello, myself Bhumika. I'll be going through security analytic tool. What is a security analytics? It basically leverages data to proactively detect, analyze, and respond to threats, enhancing an organization's security posture. By continuously monitoring and analyzing data, organizations can identify and mitigate threats more effectively, reduce the risk of security incidents, and improve their overall cybersecurity resilience. We have few steps for this. So, it basically uses data collection. It starts with the collection of vast amounts of data from various sources within an organization's IT environment. These sources can include network traffic logs, application logs, endpoint data, etc. The next step is data aggregation and normalization. Once collected, the data is aggregated and normalized to ensure consistency and make it easier to analyze. This involves combining data from different sources into a unified format, removing duplicates and irrelevant information, structuring the data for analysis. The next step is threat detection. Security analysis platforms use various techniques to detect threats with the aggregated data. Next is threat analysis. Once a potential threat is detected, it is analyzed to understand its nature, scope, and potential impact. This involves contextual analysis, correlation, and risk assessment. The next step is response. Based on the analysis, appropriate responses are initiated to mitigate the threat. This can include automated responses, incident response, and remediation. And the last step is continuous improvement. Security analytics is an ongoing process that involves continuously refining detection and response capabilities. So here we go through Falco and KubeArmor. The first one is Falco. So the Falco is basically an open source running time security tool designed to detect and respond to suspicious activity in Kubernetes clusters and other containerized environment. It is the part of CNCF, which stands for Cloud Native Computing Foundation. It is designed to monitor the behavior of applications running in Kubernetes, Linux, and other cloud native environments to detect unexpected or malicious activity. So how does this Falco do threat detection and monitoring? It uses few steps. First is system call monitoring. Falco primarily works by monitoring system calls made by applications. System calls are the fundamental interface between an application and the Linux kernel. By observing these calls, Falco can detect a wide range of behaviors that could indicate security issues. The next is rule-based detection. Falco uses some set of rules to define what constitutes suspicious behavior. These rules can be customized based on the specific security policies and needs of an organization. Falco comes with a default set of rules that cover many common security concerns such as unexpected network connections, unauthorized file access, execution of shell commands by containers, or like privilege escalation attempts. Next is real-time alerts. When Falco detects behavior that matches a rule, it generates an alert in real time. These alerts can be configured to trigger various actions such as sending notification through email, Slack, or other communication channels, or logging the event for further analysis, or triggering automated responses through integration with other security tools or incident response systems. The next step is integration with logging and notification system. Falco can be integrated with a wide range of logging and notification systems. This integration ensures that alerts are delivered to the appropriate channels and that security events are recorded for audit and analysis purpose. The last two steps are Kubernetes and container security. In Kubernetes environment, Falco is particularly used for monitoring the behavior of containers and Kubernetes resources. It can detect suspicious activity within containers, such as containers running with excessive privileges, containers trying to access sensitive host files, unexpected process running inside containers. And the last step is extensible and customizable. Falco's rule set is highly extensible and customizable. Organizations can write their own rules to address specific security concerns unique to the environment. Here we can take an example like the first how the Falco works. Monitoring a system call, Falco uses a kernel module to interrupt system call. It inspects the system's call in real time. Applying the rules, for example, alert if a customer attempts to modify. Generating alerts, if a system call matches a rule, Falco generates an alert. Then alert actions, alerts can trigger various actions like sending notifications or integrating with SIEM. The next tool is Cube Armor. Cube Armor is a runtime security enforcement. Budil, next slide, please. Next slide. So Cube Armor, it's a runtime security enforcement system specifically designed for Kubernetes environment. It provides fine-grained security controls for containers, enforcing policies that restrict the actions that containers can perform and interactions they can have with the host system. By doing so, Cube Armor helps to secure Kubernetes workloads against various security threats. How this works? This works with few steps again, like policy definition. KubeArmor allows administrators to define security policies using YAML files. These policies specify what actions are allowed or denied for specific containers or group of containers. Next is policy enforcement. Once defined, these policies are enforced at runtime. KubeArmor uses eBPF, like that is extended Barclay packet filter or other kernel level mechanism to monitor and control the behavior of these containers in real time. File system controls. It can restrict containers' access to specific files or directories. For example, it can prevent a container from modifying system files or accessing sensitive data. Next is network controls. It can enforce network policies that control the flow of traffic to and from containers. This includes restricting outbound connections to untrusted IP addresses or blocking incoming traffic on certain ports. Process control. It can restrict which processes can be executed within a container. This helps prevent the execution of unauthorized or potentially malicious binaries. Next is integration with Kubernetes. It is highly integrated with Kubernetes, making it easy to apply security policies to Kubernetes resources such as pods, deployments, and namespaces. Policies can be automatically applied and enforced as a new containers are created and deployed. And this is what is about security analytics. The next is monitoring analytics, where we monitoring tools. So where we discussed about where we will discuss about Prometheus and Grafana. Prometheus is an open source monitoring and alerting toolkit designed specifically for cloud native environments. It is originally developed by SoundCloud and has since become a part of CNCF. Prometheus is highly flexible and widely used in environments that require robust monitoring solutions, particularly in dynamic and distributed systems like microservices, containers, and Kubernetes. What are its key features? Time series data storage, pull based model, powerful query language, alerting, flexible data export, integration with Grafana. Prometheus is often used in conjunction with Grafana, which we'll be discussing later, which is a popular open source platform for monitoring and observability. How Prometheus is accessed. When Prometheus is active, you can interact with it through its web-based user interface by navigating through a local host in a web server. This UI provides several useful features like status page, graphical interface, expressing browser. It also has REST API. Prometheus also offers a REST API that enables programmatic access to its metrics data. This API is particularly useful for automation, integration with other tools, or when building custom dashboards and reports. This REST API provides various endpoints for querying data, querying over time, accessing metadata, managing alerts and targets. Next is Grafana. Grafana is also an open source platform used for monitoring visualization and analytics. It provides interactive dashboards that allow users to visualize metrics and data from various sources in real time. Grafana is widely used in conjunction with other monitoring tools, especially Prometheus, to create detailed and customizable graphical representation of system metrics. The key features of Grafana: interactive dashboards, data source integration. Grafana supports a wide range of data sources, including Prometheus, InfluxD, database, MySQL, and many others. Then templating and customization. Grafana offers powerful templating features that allows users to create dynamic and reusable dashboards. Dashboards can be customized with variables, annotations, and alerts, providing a tailored view of the data that can adapt to different needs and environments. The next is alerting. Grafana has built-in alerting capabilities that can modify and notify users with a specific condition are met within the visualized data. Alerts can also be used to trigger notification via various channels such as email or pager duty. Next is plugins and extension. The next is user management and sharing. Grafana includes user management features allowing teams to collaborate on dashboards and share within the generation. This is integrated with Prometheus. Grafana is often used alongside Prometheus to visualize real-time metrics collected from systems, applications, and services. This integration between Grafana and Prometheus is seamless and provides several advantages like real-time metrics visualization, customizable queries, correlating metrics across sources, alerting based on Prometheus metrics. Next, over to Disha.
Okay. Hi guys, I'm Disha. Coming to the recommendation systems, they are basically algorithms that are designed to suggest relevant content, products, or services to the users based on their past interactions and preferences. So these systems have become an integral part of our daily lives, as you can see, driving the user experience on platforms such as like e-commerce websites, streaming services, and social media. By analyzing large amounts of data, recommendation systems provide personalized suggestions that enhance user management and satisfaction. So we will focus on basically two specific types of recommendation models: the application specific recommendation model, which tailors policy recommendations to specific user environments, and the system based recommendation model, which detects anomalies and suggests policies to ensure system security and efficiency. Previous slide, Budal. Yeah. Coming to the application specific recommendation model. The application specific recommendation model is a rule based system that recommends optimal policies tailored to the specific environment in which an application is deployed. This model is particularly useful in environments where different applications have varying security and operational requirements. So the key aspects of this model are rule based system. The model operates based on a predefined rules that are triggered by user inputs. So these rules ensure that the recommended policies are not only optimal for the specific deployment environment, but they are also like aligned with industry standards. Second is the user as specified environments. The system takes into account various user specified parameters such as like what is the application type, security needs, and deployment specific. It then generates recommendations that ensure seamless integration and effective governance. Now, some of the example scenarios for a web-based application, the model might recommend policies that include network security protocols and data encryption and access control. For stateful application, the focus could be on like data consistency, backup strategies, and database security. So by analyzing the user provide parameters, this model ensures that the recommended policies are both like relevant and effective in maintaining a secure and efficient deployment. Now, how is this model built? Next slide. Yeah. The construction of application specific recommendation model involves like a combination of user friendly interfaces and advanced backend processing. The goal is to make the model accessible while ensuring it provides accurate and useful recommendation. Technological foundation. So Tinker for GUI. So we can use Tinker, which is a Python library, is used to create an intuitive graphical user interface. This interface allows users to input their deployment specifics with ease. So making this model accessible even though to those with limited technical expertise. And second is user inputs. User provide essential details such as type of application, the need for sensitivity screening, CI/CD usage, privilege levels, and logging behavior. These inputs are crucial for determining the policies that the model will recommend. Predefined policy sets. The model uses these inputs to search through a predefined set of policies. These policies will cover a range of scenarios, ensuring that the model can provide relevant recommendations regardless of the specific deployment details. Now, dynamic output generation. YAML file generation, the model can dynamically generate YAML files that contain the recommended policies. These files are ready for immediate integration into the deployment process. Comprehensive PDF reports. In addition to YAML files, the model generates comprehensive PDF reports. These reports basically summarize the user specifications and the recommended policies, providing a valuable reference for the future audits and documentation. So the combination of a user-friendly interface, robust policy generation, and thorough documentation ensures that the model is both like practical and effective in real world. Next slide. Now, what are the inputs for this model? So the effectiveness of the application-specific recommendation model relies heavily on the quality and specificity of the inputs which are provided by the users. Now, these inputs basically guide the model in generating relevant and effective policy recommendations. Detailed breakdown of the inputs is basically of the four types. Application type. The model first identifies whether the deployment is a web-based or a stateful application. This distinction is crucial because different application types have different security and operational requirements. For example, web-based application might require robust network security measures, while stateful application might focus on more of data management and backup strategies. Now, coming to CI/CD application. The model basically checks whether the application is a part of continuous integration or continuous deployment pipeline. CI/CD applications require specific policies to ensure continuous monitoring, like automation support, quick rollback mechanisms in case of deployment failure. These policies are essential for maintaining the integrity and reliability of the deployment process. Sensitive information screening. The model screens for sensitive information that needs to be protected. This could include personal data, financial information, or proprietary business data. If sensitive information is detected, the model enforces policies that block unauthorized access and ensures compliance with regulations such as GDPR or HIPAA. So privilege level, the model assesses the required privilege levels for the application. If elevated privileges such as root access are needed, the model ensures that the policies are in place to restrict non-privileged users from executing sensitive operations. This might include implementing role-based access control, RBAC, and audit logging to track the privileged actions. So by carefully analyzing these inputs, the model provides tailored policies that enhance both the security and efficiency of the deployment. Next slide. System-based recommendation system. So the system-based recommendation system basically focuses on detecting and responding to anomalies, particularly those related to CPU. This system is designed to identify potential security threats and recommended appropriate policies to mitigate them. Understanding anomaly detection. CPU usage as an indicator. CPU usage is a key performance metric in any deployment, and an unexpected spike in the CPU usage can indicate the range of issues, from a legitimate increase in workload or like a potential security threat. The system-based recommendation system basically monitors the CPU usage patterns to detect anomalies that could suggest that there might be security violations. Resource exhaustion, which is second one is resource exhaustion, which is denial of service attacks. One common security threat is the denial of service attack, where a malicious actor overloads the system with excessive requests, leading to resource exhaustion. The system detects these patterns and responds by recommending network policies such as rate limiting and IP blocking to mitigate the impact. Now, malware detection. Another potential cause of increased CPU usage is malware. Malware often operates covertly, consuming systems resources without the user's knowledge. The system identifies these anomalies and recommends policies focused on malware protection, such as enhanced monitoring and system isolation. Coming to proactive policy recommendations. Once an anomaly is detected, the system doesn't just stop at identification. It proactively recommends policies that can help prevent similar issues in the future. For example, if a denial of service attack is detected, the system might suggest implementing a web application firewall or increasing redundancy in the critical system. So this proactive approach basically ensures that the system remains secure and operational even in the face of potential threats. Next slide. Coming to the second type, which is the system-based recommendation model. So the system-based recommendation model operates using advanced techniques, including deep learning, to predict and respond to potential security threats based on CPU usage patterns. So this model involves several key steps. They are data collection. The process begins with data collection. A temporary pod is created to execute a command and then terminates. The CPU usage data generated during this process is collected for the analysis step. This data serves as the foundation for identifying patterns and detecting anomalies. Now you're training a LSTM based model. The collected data is used to train a long short-term memory deep learning model. So these LSTM models are particularly effective in recognizing patterns, which is over time, making them ideal for identifying anomalies in the CPU usage. The model learns from the data, allowing it to predict and detect unusual patterns that may indicate security threats. Preparing the test pod. To test the pod, a temporary pod is created, and the stress tool is used to artificially increase CPU usage. This step is crucial for evaluating the model's ability to detect anomalies and recommend appropriate policies. The results of this test help refine the model and improve its security and accuracy. Recommending security based policies. Based on this analysis, the system recommends security related policies. Now, these policies primarily focuses on network security and malware protection, ensuring that any potential threats are addressed promptly and effectively. So this comprehensive approach allows the system-based recommendation model to proactively enhance system security and efficiency by detecting and responding to potential threats before they cause any like significant damage. Next slide. So in conclusion, the application-specific and system-based recommendation models represent like sophisticated approaches to maintaining security and efficiency in modern deployments. The application-specific model tailors policy recommendations to unique needs of each deployment environment, ensuring seamless integration and compliance with the industry standards. Whereas the system-based model, on the other hand, leverages deep learning and anomaly detection to identify potential security threats and recommended proactive measures. So together, these models basically demonstrate the power of the recommendation system is not only enhancing user experience, but is also in the securing and optimizing complex deployments. They are essential tools in the toolkits of any organization looking for maintaining a robust and secure infrastructure. Now, over to Budil for the implementation part.
Okay, so my teammates gave a very good brief and very detailed brief about how the project works. So now we're going to look into an implementation of how it has been implemented in the application specific model as well as the system specific model. So this is a video recording of the model working. So as Adarsh explained, we make use of 6 VMs. One VM has been assigned as the load balancer. Two of the VMs happen to be worker nodes. 3 VMs are the master nodes. And together these form a multi-master Kubernetes cluster, which form the basis of our project. So each of these VMs are FQDN enabled. So FQDN stands for fully qualified domain network. And this is a very crucial step, as if all these VMs are not FQDN enabled, these VMs cannot talk with each other. And talking with each other is essential because the entire Kubernetes cluster is based off of communication. Each of the master node contains a kube API server, and all of the worker nodes contain kubelets. So this is how the cluster nodes talk with each other to ensure that there are enough replica sets, daemon sets, as well as all the services in a Kubernetes cluster are running appropriately at any point in time. And this is what makes a Kubernetes cluster, especially a multi-master Kubernetes cluster, especially resilient against a lot of scenarios, including a split brain strategy, because you have a majority of quorum in the form of 3 masters, as well as a setup that offers incredible fault tolerance. So let us look at this video, and here you can see that this is one of the master nodes. So this, we've taken them as one of the master nodes. There are 3 master nodes in the setup. So the master nodes have kubectl enabled, and kubectl is basically your Kubernetes command line tool. So that's what kubectl stands for. So this is how we access everything in our pod, and this is how we keep track of everything. So you want to implement policies, whatever that needs to be done in a Kubernetes cluster is maintained by making use of kubectl. So this is the first command that we've run here. And as you can see, kubectl get nodes. So this is to get the nodes in the cluster. And as it is seen, there are the name of the nodes. You may notice that I mentioned that we have 6 VMs, but here there's only 5 visible. That is because the 6th VM, which is the HA proxy load balancer, that is not part of the Kubernetes cluster per se, in the sense that it does not show up in the as part of the nodes in the Kubernetes cluster, but that is also a part of this cluster, since that is what directs the traffic and balances the traffic as well as the load. So these are our nodes. So the 01, 02, and 03, these three are our work master nodes. And you can see that roles have been given as control plane. So Kubernetes assigns roles, and under roles, master nodes have the name as control planes, while worker nodes do not have any roles assigned to them. And you can see the age, that is when they were initially initialized, as well as the versions. So this is, and we can also see the status. So when a node is ready is when a node can run replica sets, daemon sets, services, whatever that is required, pods. So when it is not ready, and even if there is one thing that is missing in a node while configuration of the node, then the status pops up as not ready. So this is about kubectl get nodes. So let's look at kubectl get pods. So kubectl get pods a slash hyphen a. This is used to get all the pods that are running in a cluster. So as you can see, there are multiple pods that are running here. So some are kube system pods. So they are classified on the basis of namespace. So all these pods have a particular namespace. So that is what they start with. You have a namespace, and then you have the name of each of these specific pods. So these pods have a name. They have some shown under the default namespace. For example, our Nginx deployment shows under the default namespace. They have a name. And then you can see they're ready how many of these pods exist. So some pods have multiple copies, some pods have a single copy. And the ready shows how many of those pods are ready, in the sense how many of them have been deployed. Then you have the status. So status shows whether a pod is running. A pod may be running, it may be initialized, it may have been completed. Completed in the sense a pod may have, the running of a pod may be completely completed. And restart, what restart show is how many times a pod is restarted. So Kubernetes has this feature where unhealthy pods are naturally pruned and they are reinitialized without any loss of data. So this sort of killing of unhealthy pods as well as initialization of the same pods again is done in a very lossless manner. And here you can see that restart specifies how many pods, how many times the pods have been reinitialized. That's what the restart shows. And age shows when the pods have been initialized into the cluster. So this is a gist into Kubernetes get pods A. So you can see there are multiple pods. We have Prometheus pods, we have Falco pods, we have Calico. There's the etcd. So etcd is the data store. Then you have kube proxy. There's kube proxy, there's kube API server, there's kube controllers. These are specific kube controllers, kube API servers, kube schedulers are specific to the master nodes. So then you can see, so this is our Nginx deployment. So this is just a dummy deployment that we have taken for Nginx. So there's nothing special about this deployment. This is just to implement the next few things on our cluster. So that is what this deployment is. So this is our Nginx deployment, and it can be accessed through the any of the IP addresses of the VMs. And these are the security tools. So as Bhumika explained earlier, we've used Falco and KubeArmor. So here we're going to see a quick and brief info about KubeArmor. So this is how KubeArmor is specified in the Kubernetes cluster. We run KubeArmor. KubeArmor can be run on the host But in this case, we have run KubeArmor as a daemon set, and we have used it specifically for Kubernetes in order to, give it maximum compatibility. So these are all the pods: KubeArmor, AppArmor, container, controller, operator, relay. These are just the other information. So KubeArmor is a preventive security tool. So you can see here that when you put the commands for KubeArmor come in the form of KArmor probe. So when you do this, you can see that you have the namespace, default posture, visibility name, and the policy. So KubeArmor also helps you implement policies. So you can deploy policies for each and every specific pods. And each of these policies are deployed in the form of .yaml files. So this is just we have tried unauthorized access, and you can see here that the logs for KubeArmor shows up. So these are the logs. So you've been given an alert along with the appropriate timestamp. So it also mentions which pod has been accessed in a malicious manner, which worker node it has been hosted on, the cluster name, the namespace, and it gives a very detailed log. So this is the logging ability of KubeArmor. So it also, as you can see, you can also see that the command has been terminated, which means that since the policies have been implemented, KubeArmor has performed its job of cluster hardening and has managed to remove that has managed to remove the malicious threat that was existing to the cluster. This is now a simple demonstration of Falco. So Falco does the exact same thing, but Falco only gives you a runtime security log, unlike Cuba, which also prevents. So here, Falco is just telling us that there has been an unauthorized access. And even here, Falco can be implemented directly on the VM, but we have again chosen to implement it as a daemon set on the cluster. Moving on. So we're coming into the application specific recommendation system. And this is as Disha mentioned. So we have implemented this as a Linux executable. So a Linux executable which takes this form. So the user fills out a few questions based on what they need. So web-based or stateful. And then if they choose stateful, they have the option between MySQL, MongoDB, as well as PostgreSQL. Then once they're done, we ask them whether there's any sensitive information that needs to be screened, whether it's a CI/CD application, whether they need root access, whether the application is going to generate logs. And then we recommend the policy. So the policies have recommended. So we have taken a set of policies which have been implemented in Python by making use of a dictionary. So based on what the user asks, we map those policies to what we feel is most apt to them. So the algorithm takes care of that. And then we also give them a table, a tabular representation of what they need and recommended policy, as well as a description of that policy. And for additional reference, what we also do is that we create a PDF file. So what this PDF file does is it contains a policy recommendation. So it contains the user inputs, what the user inputted, the recommended policies, which include the condition for the policy themselves, the description for the policy, and that in essence, all the policies that have been recommended. So this is for the user's documentation purposes. Coming to Prometheus, Prometheus is a monitoring tool, and as mentioned here, it is implemented in the form of a pod. So when we have to access Prometheus, Prometheus is just a logging tool. In order to visualize the data that Prometheus offers to us, that needs to be done by making use of Grafana. So Grafana is also here, also Prometheus and Grafana are implemented as daemon sets. So here you access them to the local host, and when you come to Grafana here, the interesting thing here is that since it's integrated with Prometheus so well, you can see the CPU utilization requests, CPU limits, commitment, memory utilization, memory requests. So this gives a very, very detailed and in-depth understanding of what is going on in our Kubernetes cluster. This is very good in that regard. But where Prometheus really shines is that it helps us in the training of the system-based recommendation model. So here, as Disha mentioned, we have made use of a LSTM model. So what this LSTM model does is it collects data, and for these LSTM modules, the data comes from Prometheus. So what Prometheus does is that Prometheus scrapes data from the cluster at regular intervals. So each pod is supposed to have a specific CPU utilization rate at any given time. And if that pod exceeds that CPU utilization rate, it is considered a malicious pod and it poses security threats. So it could pose a security threat in the form of denial of service attack, or it could also form a malware detection issue. So what we do here is we train the LSTM model based on the data that we scrape from Prometheus. Right. So then to simulate what happens and to show how this works. So we have already trained a model based on this, and we have kept the model based on logs that we have taken for Prometheus. So we have trained it based on data, regular data for a particular pod for a period of 30 days to give us a very wide range for the LSTM to learn. So here, this is the policy. So this is before the malicious pod is deployed. So here you can see that the CPU usage is normal, but once the malicious pod is applied, what happens? You can see that a high CPU usage is detected, which means that there's a issue. So we recommend two types of policies here. One is a network policies, which is a KSP network control is KUBERNETES security control. So we have a network policy and we also have a malware policy. So based on what the client needs, what the user needs, the policy is recommended and it's also applied into the system. So the Python script that you've written here, so the Python script contains the LSTM module. It also contains the API endpoint that leverages the data that is scraped from Prometheus. So from that, we have trained a model and the weights have been assigned. So based on these assigned weights, the model makes a decision. And when it detects high CPU usage, it creates two different network and malware policies and it implements them in order to reduce that and eliminate that threat. So like this, we take care of not just the application-based security for a Kubernetes cluster, but we also take care of the system-specific details, and we offer security on the system side as well. So this provides a very robust as well as very, very thorough and comprehensive security, which in turn secures any Kubernetes cluster, which is essential in this era of cloud computing. So I hope this was helpful. Thank you.